Hello, everybody. So after the green kernels and the Mercer kernels, today we're going to introduce a third broad class of kernels called shift invariant kernels, which will allow us to study new kernels that we did not have the occasion yet to study in detail, like the Gaussian kernel, and describe the RKHS of the Gaussian kernel. So to motivate this work, remember, for example, that when we studied Mercer kernels, there were a few conditions, like it had to be a continuous kernel on a compact space. And so, for example, what we saw with the Mercer theory does not apply to the Gaussian kernel on R, which is typically something we use very often. And if you go to the, fundamentally why Mercer theory does not apply here is because the operator associated to a Gaussian kernel over R or RD is not compact, and therefore, for example, the spectral theorem would not apply and would not lead us to a countable sequence of eigenfunctions and eigenvectors. So we need something else, and this is what we will do today. All right, so what we will discuss today are translation invariant kernels, which sometimes are called shift invariant kernels. So even though the goal is typically to work on R, on RD, so the vectors and real numbers, we will start with something slightly easier, because then we'll be able to prove everything. It will be technical a bit, but at least we will prove everything in detail. And then we'll move on to the continuous setting, and I will spend less time on the proofs. All right, so to start with, instead of considering a kernel defined over RD, we will just define a kernel defined, we'll just consider a kernel defined on integers, relative integers, so positive and negative integers, meaning the space is Z. And so we consider kernels defined over Z, meaning a function K that takes as input two integers and output a real number. And so we will say that such a function, so if it's a kernel, we say that the kernel is translation invariant if and only if the value of the kernel between two integers only depends on the difference between the integers. Like you would say the kernel between 5 and 12 would only depend on the difference between 5 and 12, which is 7. It would be a number, a function of 7. All right. So in particular, this means that when we consider the translation invariant kernels, they are completely characterized by just a sequence of numbers, which we will call an when n is in Z. That characterizes the value of the kernel between two integers x and y as a index s x minus y. All right, so we will say that this sequence is positive definite if and only if the kernel K as a kernel over Z is positive definite. So notice that to be positive definite, there are two conditions on K. K should be symmetric, and K should satisfy the fact that the Gram matrix is positive semi-definite. So for the symmetry, we immediately see that K of yx is equal to A index y minus x. So K will be symmetric if and only if the sequence A is symmetric around 0, meaning AT is equal to A minus T. Right, so this would be a first constraint that we need to have on A for the kernel to be positive definite. Now the question is, what can we say about the sequence A to make sure that K leads to positive semi-definite Gram matrices? And so what we will state and prove is now a precise characterization of the sequences A that lead to positive definite kernel. And this is a theorem proved by Erglotz. So we call that Airglass Theorem, which reads as follows. It tells us that a sequence of numbers, an, is positive definite if and only if it is the Fourier Transform of a positive measure, mu, in the space M of t. So I need to explain a bit what is all these Fourier transform and what is M of t. This will be done in the next slide. But basically, t is just the interval 0 to pi, right? And M is the space of measure. So think of mu as a measure positive measure on the interval 0 to pi. And the Fourier still-Jess is just the Fourier transform of a measure that we will define formally in the next slide. But so before going to the technical details, what's important to see here is that this fully characterizes exactly all positive definite kernels which are translation invariant. These are the functions which are Fourier transforms of positive measures, right? So we will see later an extension of that to to kernels defined on the real space. But already here, we have a complete characterization, and later we will see that we can also get a characterization of the RKHs. All right, so first, let's now try to clarify precisely the meaning of this theorem, in particular the Fourier transform, and prove it. So what is a Fourier transform? By the way, I will, instead of saying Fourier still-Jess, I will just say Fourier transform, because basically here we just want to talk of the Fourier transform of measures. So probably you know, and I invite you, to check that you know a bit about Fourier transforms. You know that Fourier transforms can be defined on different spaces. It can be defined on the space of periodic functions, then on the space of integrable function on R, then on the space of L2 functions, etc. So when you build all the Fourier transforms, what we need for the theorem is a notion of Fourier transforms, not for functions, but for measures. And so basically, this definition on this slide describes what is the Fourier transform of a measure. It just, so mu, if mu is a measure on the torus, and again, the torus is just the interval 0 to pi, but when we identify 0 and 2 pi, so think of it as defining the periodic functions. Then we say that, so we call the Fourier transform of mu the set of coefficients, so it's discrete because we work on the compact set 0 to pi, defined by mu hat of n. So the nth Fourier coefficient is just 1 over 2 pi, which is just useful for normalization, times the integral between 0 and 2 pi of exponential minus int d mu of t. Right, so it's really the standard formula. Usually you see this formula not with d mu of t, but with f of t dt, and you call that the Fourier transform of f. Here we have the same, except that this is now defined not only for functions, but for measures. And there are measures which are not functions, right? Like the Dirac measure. All right, so a couple of things you need to, for information is that, so t is the torus when 0 to pi is identified. M of t is a set of measures, and to be more precise, we talk of the Borel measures. So these are just the measures defined on the open sets. This is standard. And just for information, something that we will use in the proof is that we can characterize all the measures in M of t as the dual space of C of t, where C of t is a set of continuous functions on the torus. So remember that because we identify 0 and 2 pi, continuous means in particular that C, the function in 0 has the same value as in 2 pi. Right, and so we can characterize all such measures in M of t as the continuous linear functions from C of t to the set of complex numbers, or we'll just use real numbers here. Right, in a sense that for any continuous linear functionals from C of t to R, there exists a measure mu such that the integral of f of t d mu of t is equal to the linear function. And this thing is called the Riesz theorem. All right, so this is the Fourier transform. And so now let's try to prove the Herglotz theorem that relates the Fourier coefficients of a positive measure to the fact that the kernel is positive definite on Z. So sorry, before proving it, let's give a couple of examples to check at least that there are some easy cases which fall in the theorem. So the first one is suppose for the measure mu, remember mu is a measure over the interval 0 to pi, if you just take the uniform Lebesgue measure on it. So mu equals dt. Then what's the Fourier transform of it? Well, you just compute it with the formula. So it's mu hat of n is 1 over 2 pi times the integral on the torus of exponential minus int. Here I just write plus int, but it's the same because we are symmetric. And so this, we know that obviously when n is equal to 0, this gives 1, because exponential int is constant, is equal to 1. And when n is non-zero, then the integral of any sine and cosine over the full circle is equal to 0. Right? So the corresponding sequence an is equal to 1 for a0 and to 0 for all other values of n. And so in terms of kernels, this means that the kernel we get between two integers x and t is equal to 1 if x is equal to t and 0 otherwise. Right? So this is the classical, sometimes we call it the Dirac or the diagonal kernel. It's just a kernel that says that x and t are all different if x is different from t, otherwise they are the same. And so this is a translation invariant kernel, and we see that indeed the diagonal kernel is the Fourier transform of a positive measure on the torus. Now let's take a second extreme example. Remember I said that measures are a bit more general than functions. So let's take a measure which is not a function, which is not a measure of the form f of t dt. Let's take the Dirac measure in 0. So we take for mu the Dirac measure in 0, delta 0, and we multiply by 2 pi c, just you will see why, where c is a non-negative number. So if we compute the Fourier transform of that one, then for any n, we can compute mu hat of n as 2 pi c divided by 2 pi, so the 2 pi cancels, times the integral between 0 and 2 pi of exponential int Dirac in 0 of t. And so the value of the integral is just the value of the function exponential int in 0. So this is 1. And so we get 1 times c, which is equal to c, the constant. Right, so the kernel we get as the Fourier transform of the Dirac is a constant kernel. And so we know that indeed when a constant is non-negative, then it's a valid positive definite kernel, which is translation invariant because it only depends on the difference, x minus t. In fact, it does not even depend on it. Right, so this shows in particular that in order to be able to include the constant kernel in our result, we really need to be able to talk of Fourier transforms of measures and not only of Fourier transforms of functions, because we need to include the Dirac in order to recover the constant kernel. All right, so let's try now to prove Herglotz, the theorem of Herglotz. Ergot theorem is a if and only if statement. So K is positive definite if and only if the sequence an is the Fourier transform of the positive measure. So we have two things to prove. And one of them is quite easy. It's written in this slide. So the easy part is to prove that if an is the Fourier transform of a positive measure, then the kernel is positive definite. So we already discussed the symmetry. The only property to check is if you take any integer n, any sequence of integers x1, xn, and any sequence of real numbers z1, zn, we need to compute the double sum of zi, zj, kernel between xi and xj. So this is what we do here. We replace the kernel between xi and xj by a xi minus xj, because this is the definition of the kernel. Notice that here I consider, even though the z are real numbers, the proof would work even if they are complex numbers. So it's slightly easier to manipulate complex numbers here instead of sines and cosines. So I put ci times zj conjugate, but think of it as just the same without a bar for z. Okay, so in order to prove that this is non-negative, we just replace a by its property, which is to be the Fourier transform mu hat of xi minus xj. And so we replace a index xi minus xj by 1 over 2 pi times the integral of exponential minus it times xi minus xj d mu of t. Then the magic occurs. The magic is just to notice that the exponential of a sum is the product of the exponentials. It's easy, but it's super important in this proof because it allows us to separate xi and xj in two different terms, the product of exponential. And then when we just inverse the double sum and the integral, we can factorize the double sum and recover that what we measure is just 1/2 pi times the integral according to d mu of t of the squared module of a complex number, which is the sum of zj exponential minus I xjt. And so because mu is a positive measure, and because the module of a complex number is a positive number, this integral is non-negative. Right? So easy proof, and the crucial thing here is just that the exponential of the sum is the product of the exponential. So this is how there is an interplay between being translation invariant and using the Fourier transform, basically. The other direction, it's slightly more complicated, but I must say it's not conceptually much more difficult, but technically a bit longer. It takes 4 slides, so I will go a bit quick on it, but you're welcome to take more time to study the slides by yourself. Just to give you an idea of what the proof does. So here, we start from a sequence, an. We assume that it's positive definite, and the question is it the Fourier transform of a positive measure, right? So in order to answer positively, we need to guess what would be the measure. In fact, it's not complicated, because if you think of what could be a measure such that an is the Fourier transform of mu, we know that going from mu to an is called the Fourier transform, but we know that there is also something called the inverse Fourier transform, which allows you to reconstruct the measure from its Fourier coefficient, right? And so it's quite evident that if an is the Fourier transform of a positive measure, then this measure mu has to be, roughly speaking, the sum of an exponential int. And so the question would be, can we make this measure? I can prove that it's positive. But doing it just directly, if you try it, you will see that it's not trivial to show that it's positive. So basically, the 4 slides do it using some approximation to make sure all the things are technically correct. So let's see how this works. Well, on this first slide, we prove something which is almost what I said, but with some small difference, which will be that we will need to correct in the next slides. So if you look at the sequence of 3 inequalities on this slide, so the big block of equations in the second half of the slide, if you just look at the message that it shows that on the left you have 0 smaller than something, so we show that something is non-negative. And if I'll come back to the equations maybe, but if you look at the last thing, so what is non-negative, is basically there is a factor 2n plus 1 that we don't care about. But then there is something which we call sigma 2n of t, so it's a function of t, which is non-negative. And if we look at what is this function sigma 2n of t, you see that it's a sum for k over z of a max of something. I'll come back to that later. But after the max, there is ak times exponential ikt. So basically, if there was not a max term, the sigma 2nt would be just the sum of ak exponential ikt. And this is what I said before is the perfect measure we want to recover, because this is intuitively the measure such that its Fourier transform are the ak's, right? So we don't exactly, we have the max term, which is important here. You'll see why. But up to the max term, the message of this equation is that the mu that we want, we show that it's non-negative. And so this is really the important part of the Ergot theorem to show that this measure is non-negative. So let's first quickly study how this equation is obtained. Well, this equation, so the fact that sigma 2n of t is non-negative, is obtained by using the fact that an is a positive definite sequence, and by choosing a specific Zn. So there is a definition of Zn, which is defined as 0 when n is large, or exponential int when it's small, smaller than a constant capital N. And so with this, so this is just a trick, I mean, a particular choice of Zn. And so with this particular choice of Zn, when we write the property to be positive definite for the kernel, we just write that the sum of over k and L of kernel between k and L, so A index k minus L, times Zk times Zl conjugate, is non-negative. And then it's just a question in 3 equations of replacing Zk by and Zl by their values, reorganizing the term, and obtaining sigma 2n of t. Right, so just take the time to redo the computation by yourself, but in this equation, we use the fact that an is positive definite in order to derive that sigma 2n of t, which is something like what we want, up to the max term, is non-negative. So maybe let's look a bit at this max term. You notice that this max term is just a max between 0 and something, so it's always a non-negative thing, right? Because it's the max between 0 and something else. And so the something else is 1 minus k in absolute value divided by 2n plus 1. So the important thing here is that if you fix a k, for example, k equals 5, then 1 minus 5 over 2n plus 1 is a number. But what we'll do later is, intuitively we want capital N to become larger and larger. There will be some convergence. And so we notice that when n gets larger, then the term k over 2n plus 1 converges to 0. And so morally, the max of 0 and the second term converges to the second term, which is 1. Right, so the max term, think of it as something that will disappear when n gets large, because it will converge to 1. And so sigma 2n of t intuitively will converge to the sum of ak exponential ikt. All right, so this is, I gave a lot of intuition, but for the moment, what's written on the slide is just correct with capital N, sigma 2n of t. And then the rest of the proof works as follows. There are a couple of technicalities yet. So the first one is we can formally define, for sigma n of t, we can define the measure mu n as sigma n of t times dt. As we have seen in the previous slide, sigma n of t is a non-negative number for any n and any t. So the measure mu n is a positive measure. We can compute its Fourier transform if we want. It's not exactly equal to, so mu hat capital N of n is not exactly equal to an. It's an times this max, which I said converges to 1 when capital N is getting large, but it's not exactly an. It's almost an. And something that we will use later is that remember that as a barrel measure, mu n defines a linear functional over the space C infinity of continuous functions over 0 to pi endowed with the supremum norm. And so if you want to compute, we can compute the norm of mu n as a function. And the norm of mu n is the supremum over continuous functions f with max norm bounded by 1 of the function mu n of f, which is the integral of f of t times mu n d mu n of t, so sigma n of t dt. And so because mu n is positive, the supremum is reached when f is a constant function equal to 1, in which case, when we do the computation, we obtain just a0. Right, so this means that for any capital N, the function mu n is a positive measure, and its norm is equal to a0. It's a bound, and so for any n, it's bounded by a0. All right, so the reason why we estimated this norm is just that then we will extend and try to, we will try to take a limit when capital N gets large. And to take the limit, we just consider mu n as a function, so as a functional not over all the continuous functions, but to start with just what's called the trigonometric polynomial, which are defined as a sum of bk exponential ikt, whose Fourier coefficients are just the bk's. And the reason why we do that is that for trigonometric polynomials, we can compute exactly the values of the integral of p of t times d mu n of t. This is what we do in this slide. Importantly, the trigonometric polynomials are dense in the space of continuous functions. So this will be our way, to estimate, to go to the limit over mu n, seeing it as a functional over continuous functions. But to do that, we will use the approximation mu n applied to trigonometric functions, trigonometric polynomials. All right, so I will not detail the calculus here. You can just redo them by yourself. But what's important is that for any trigonometric polynomial, when you compute the integral of p of t times d mu n of t, and then you obtain something, and you can take the limit when n tends to infinity, and this limit gives you a functional which is the sum over k of ak p hat of k. So p hat of k is the Fourier transform of the polynomial. Right. So here we have been able to take a limit of mu n, seen as an operator. Now the fact that now if we come back, if we start from the end, if we say, okay, let's look at the operator, the sum of ak p hat of k. This is obviously a linear function over the space of trigonometric polynomials. Moreover, because we've seen that the norm of mu n is bounded by a0, then the norm of this functional operator is also bounded by a0. And so this operator is a linear functional with norm bounded by a0. Now we can go to the limit in terms of functions because we have an operator defined over trigonometric polynomials with bounded norm. So at the limit, this creates an operator over continuous functions because, again, the space of trigonometric polynomials is dense in the space of continuous functions. And so now psi becomes a continuous functional, so linear functional, over the space of continuous functions defined over the torus. And now we can apply the Riesz representation theorem that tells us that there is a measure mu with bounded norm, right? Because it's a limit, such that the operator psi of f for any continuous function is the integral between f of t and d mu of t, right? So finally, you see, this is how we take the limit of the mu n. But to take the limit of mu n, we take the limit of mu n over the polynomials, then we extend from the polynomials to the continuous function, and then we use Riesz representation to obtain the existence of a mu that will correspond to the functional that was obtained by taking the limit of the functional applied to polynomials. All right, so we have a mu. Now the question is it the mu we are looking for, in the sense that is the Fourier transform of this mu equal to A, and is it positive? And the answer to both questions is yes, and it's not a surprise. So to check that the Fourier transform of mu is equal to A, we just compute the Fourier transform. So we want to compute the integral of exponential int d mu of t. And so this is just psi of exponential int. And because exponential int is a trigonometric polynomial, is the simplest one, we can come back to the definition of psi for trigonometric polynomials, and it gives us exactly an. Right, so the Fourier transform of mu is A. And the fact that mu is non-negative just comes from observing that the non-negativity that we had initially of mu n over polynomials passes to the limit. Right, so if f is non-negative, we can write the integral of f of t d mu of t as psi of f, which is the limit of psi of Pn, where Pn is a sequence of trigonometric polynomials that converges to f in supremum norm. And then we can approximate psi of Pn by what I call psi k, which is just obtained by the measure mu k. And this one was non-negative. All right, so it was a bit technical, but you see that we were able to build, to characterize exactly, I come back to the theorem, the translation invariant kernels on Z, and they are related to positive measures on 0 to pi through the Fourier transform. So it seems a bit abstract, but what we will try to do a bit later is also not only to say if a kernel is positive definite or not, but to characterize its RKHS. And this will be possible, but before that, we need to extend a bit this result from Z to R, basically trying to see if we can do the same kind of computation for real valued, for kernels defined on real numbers or vectors, which typically could be the case of the Gaussian kernel. All right, so let's try to make the same story, but replacing Z by RD. So the same story means the same definition. We say that the kernel defines for real vectors is translation invariant or shifted variant if and only if it's a function of the difference. So if k of xy is a function phi of x minus y, for, where x minus y is just the difference between the two numbers of the two vectors. Right, so as before, for k to be symmetric, we just need phi to be even. So phi of t should be equal to phi of minus t. But the question is, what constraints or how to characterize the functions phi such that the kernel phi of x minus y is positive definite? And so the answer is a theorem. So it's a slightly partial answer because there is a constraint of continuity on phi. But basically, the equivalence of Ergot's theorem exists on RD, and it's called Dorner Theorem. And this one is important. So I think this is the main theorem for today's lecture. If there is one thing to remember, it's this theorem. So Dorner Theorem tells you something similar to Ergot's. It tells you that a continuous function phi is positive definite if and only if it is the Fourier transform of a symmetric and positive finite parallel measure mu. All right, and I'm sorry, I see there is a typo here. So it's not a measure defined over the torus. It's a measure mu defined over RD. I will correct the slides. Okay, so it looks quite similar. There are a couple of differences with Ergot's theorem. So first, the important word here is Fourier transform of a positive measure. The fact that it's symmetric, it's just for phi to be real valued. So this is not something new. Now, the only slight difference is that on the side of phi, there is this small constraint that phi should be continuous, right? So there was no notion of continuity for z because these are just a sequence. But now we can just give a result for continuous functions phi. And on the side of mu, the corresponding new constraint is that mu should be finite, right? So in particular, this theorem does not cover the Dirac kernel, the diagonal kernel, that would require some non-finite measure. And in fact, in that case, the theorem is not true if we remove the word continuous and finite. Right? But so except for these edge cases, the result is basically the same. It tells us that if you want to know if a kernel K defines as phi of x minus y is positive definite, you just need to check if phi is the Fourier transform of a positive measure. And by the way, if here the question is phrased as is phi the Fourier transform of a measure, then often, under some assumptions on phi, if phi is the Fourier transform of someone, then you can recover the someone by doing the inverse Fourier transform, right? So typically when you start from phi, you can do the inverse Fourier transform and check if what you get is a positive measure. All right, so we will not go through all the proof. I think it's quite similar to Ergot's, but just let me tell you that everything is in the slides. So here in this slide, we recall or we give you the definition of the Fourier Stieltjes transform for measures on RD. is pretty similar to the definition we had on the torus, except now we do the integral over RD and not over 0 to pi. Notice that, wait a second. Yeah, just notice that here I don't know what happened. Sorry, my computer just froze, so I assume that you lost the slides. Okay. Yeah, so it's pretty similar to the Fourier transform over Z. So the only difference is that now we do the integral over RD, and for some reason we don't divide by 1 over 2 pi to the d this time, but because then the normalization constant will be in the inverse Fourier. But it's not a fundamental change. Right, so again, here we talk of Fourier transforms of measures. And like before, we have also the story that the space of Borel measures is the dual space of the space of continuous functions that vanishes at infinity, and we still have a Riesz theorem. So it's all technical details, etc. I've just mentioned that, as before, there is one direction. This I can skip. There is one direction in the proof which is easy. It's that if phi is the Fourier transform of some mu, which is positive, then the kernel is positive definite. I will not read out the proof, but it's exactly the same as before. The only difference is that now the integral is over RD and not over 0 to pi. But it's the same trick that we use here, is the fact that the exponential of the sum is the product of the exponentials, right? And this allows us, again, to obtain the non-negativity of the quadratic form in Z. For the other direction, I will just skip it. Please have a look if you're interested. I just mentioned that it's a bit like before. We need to start from phi and compute or at least show the existence of a measure, positive measure, such that phi is the Fourier transform of the measure. You have to be careful. So we again use Riesz representation theorem, which is used in this lemma to show that if phi satisfies some inequality, then it is the Fourier transform of a measure. And then we also use in a proof. So the idea of the proof is to start from functions defined over discrete sets, then use Erglotz theorem, so the theorem that we have seen already over Z, and then somehow do a limit from discrete to contiguous. Right, so look at it if you're interested. Everything is in the slides. All right, so up to now, what we have is over Z and over R, even RD, we have a characterization of the translation invariant kernels, and we know that k of xt equals phi of x minus t is positive definite if and only if phi is the Fourier transform of a positive measure. Now, what we show now is that not only do we know that, but once we have this, so once we have a phi which is the Fourier transform of a positive measure, then under a couple of additional assumptions, we can describe the RKHS of the kernel using the Fourier transform of phi. So this is what's written here. Here we assume a couple of more things about phi. We assume that phi is integrable over RD, and that its Fourier transform f hat is integrable as well. So, up to now we focused on Fourier transforms of measures. This is the generic setting for Dorner Theorem. But to describe the RKHS, now we restrict ourselves to a subclass of functions. So phi is not a measure anymore because f is in L1 and f hat is in L1. Now the Fourier transforms are just Fourier transforms of functions. Okay, and in particular, if f is the Fourier transform of a function, then the function is the inverse Fourier transform of phi. So it's phi hat. And in that case, so for such phi's, then the RKHS is the subset of L2, the subset of functions in L2 f, such that the integral over RD of f hat of omega square, so it's the Fourier transform of f, divided by phi hat of omega, is finite. So there is, of course, a scaling term, 1 over 2 pi to the d, which is not important. But so this characterizes the functions in RKHS. And in addition, when this integral is finite, then the value of the integral is the squared norm of f in the RKHS. Or in other words, as you see in the slide, the inner product in the RKHS between f and g is defined by, up to a scaling factor, the integral of f hat of omega, g hat of omega. Here we use the conjugate because this could be complex numbers, divided by phi hat of omega d omega. Notice that phi and phi hat are real valued here. Okay, so is it useful? We will show that yes, it's useful. For example, it allows us to characterize the RKHS of the Gaussian kernel, of the Laplace kernels that we will see, etc. But before looking at specific kernels, I think the take-home message of this theorem, which is the second important slide of today's lecture after Dorner Theorem, is that the norm in the RKHS of a translation invariant kernel for a function f is expressed in terms of the Fourier transform of f. So you can think of the Fourier transform as a way to decompose f over different frequencies. You know that when you have f of omega, often we say that omega is a frequency, and so when omega is large, it means that, and if f hat of omega for large omega is a big number, it means that in f you have a lot of high frequency components. And in the opposite, if f is a smooth function, then in terms of Fourier transforms, most of the f hat is concentrated over small values, small frequencies. Okay, so this is typically why we use Fourier transforms, is to characterize the smoothness or the components of f in terms of frequency, like high frequency and low frequency components are split in the Fourier transform because the frequency, so the omega is the frequency. And so what we see here is that when you use a translation invariant kernel characterized by a function phi, then phi plays the role of amplifying or not the energy of f, so the f hat of omega, at different omegas. And so, for example, imagine you have some range of omegas on which phi hat of omega is very small. Then you see that for those omegas, because you divide by phi hat of omega, the RKHS norm can get very large if f hat of omega has large values over that range. Right? So you can think of phi, so the choice of the kernel, as a way to decide which frequencies you penalize in the RKHS norm. We will make this a bit more clear on specific examples in a few slides. So before that, let's try to prove this theorem. So to prove that this is the RKHS, we need to prove that H is a Hilbert space of functions, then that Kx is in H for any x, and then that F inner product Kx is equal to f of x for any f and any x. So the fact that we have a Hilbert space of function, I will not do it. There is nothing super interesting there. It's just true. You can try to prove it by yourself. I will just focus on the thing which are a bit specific, which is it true that Kx is in H? In the sense that, is it true that for Kx, the integral of Kx hat squared divided by phi hat of omega is finite? And the second will be, is it true that f inner product Kx using the second formula is equal to f of x? So for that, let's just notice that Kx by construction is equal to the function phi of x minus y when you fix x. So we need to compute Kx hat in order to compute the inner product, for example, or the norm of Kx. So when we compute Kx hat of omega, just using the fact that Kx is equal to f of x minus y, we just can do a small change of variable in order to obtain that the Fourier transform of Kx is the Fourier transform of phi, so phi hat of omega, multiplied by the complex number exponential minus I omega transpose x. Right, so in particular, this means that in terms of module, the norm, if you want, so the module of kx hat is equal to the module of phi hat, because the module of the exponential is equal to 1. And therefore, when we want to compute the integral of kx hat of omega squared divided by phi hat of omega, then we just obtain the module of phi hat of omega on the top, which is just phi hat of omega squared, and divided by phi hat of omega. So one of them disappears, and we just obtain the integral of phi hat of omega. And remember that in the assumption of this theorem, we assume that phi and phi hat are integrable, so this is finite. And so we get that kx is in the space capital H. For the second point, let's take any function f in H, and let's take any point x in Rd, and try to compute f inner product kx. So we just use the formula. It's 1 over 2 pi to the d times the integral of kx hat of omega times f hat of omega with the bar divided by phi hat of omega, right? So here we use again what we had before, so the fact that kx hat of omega is equal to exponential minus I omega transpose x phi hat of omega. The phi hat of omega cancels with the phi hat of omega at the denominator. And what we get is just the integral of f hat of omega conjugate times exponential minus I omega transpose x d omega. And so all this is the conjugate of the integral of f hat of omega times exponential plus I omega x. And this thing is exactly the inverse Fourier transform. So it's the formula for the inverse Fourier transform. So this thing is exactly the conjugate of f of x, which is equal to f of x because f of x is real valued. Right, so here we use the inverse Fourier transform, which is valid because we assume that capital H is a set of integrable and continuous functions. So on integrable function, we have the inverse Fourier formula. And so this shows that we have the RKHS. Okay, so this theorem is correct. The RKHS of translation invariant kernels is characterized in the frequency domain, so in the Fourier domain, by these equations. So now we can move on and look at specific examples, which I promised to look at since the beginning. So the first example is the Gaussian kernel. And finally here, I think it's something that we were waiting for since several weeks. Finally, we have a clear characterization of the RKHS of the Gaussian kernel. We know that the Gaussian kernel is positive definite. There are different ways to prove it, but we still don't know. I mean, this is the first time we see it, why you may want to use it and what it encodes as prior knowledge. So the story here is that the Gaussian kernel, I just do it on R, but you can imagine doing the same analysis on RD, just replacing the parentheses by the norms. So for real numbers, the Gaussian kernel of bandwidth sigma is the function k of xy equals exponential of x minus y square minus x minus y square over 2 sigma square. So this is, as promised, a translation invariant kernel. It depends on x minus y, and so we need to look at the function phi of t, which would be exponential of minus t square over 2 sigma square. Question, so is it positive definite? Then the question is just, is the Gaussian function phi the Fourier transform of a measure? In fact, no, a Gaussian is integrable in L2, so we can apply the inverse Fourier transform and notice that the Fourier transform of a Gaussian is another Gaussian. So phi hat of omega is a Gaussian exponential minus sigma square omega square over 2. And so, by the way, this is something you should do as an exercise. Compute by yourself the Fourier transform of a Gaussian. And you see that the only difference between the two Gaussians is that the sigma square is either at the numerator or denominator. So in a sense, if you do the Fourier transform of a narrow Gaussian, it's a broad Gaussian. And the Fourier transform of a broad Gaussian is a narrow Gaussian. And when sigma squared is equal to 1 is itself. All right, so phi hat of omega, so the Fourier transform of phi hat is x. So phi of x is indeed the Fourier transform of a positive measure because Gaussian is a positive function. And so this proves that K is a positive definite kernel. So we knew that already, but this is a new proof that the Gaussian kernel is positive definite. Now, the additional thing we have now is that we can describe the RKHS of the Gaussian kernel using this general characterization. Right, so we have a phi which is integrable. It's Fourier transform as well. So because phi and phi hat are Gaussian, so we are in the context of the theorem. And so we can say that the RKHS is a subset of L2 that consists of functions which are integrable, continuous, and such that so the integral of f hat of omega square over phi hat of omega is finite. And then the norm in the RKHS is this finite number. All right, so we see that here we just need to plug phi hat of omega. And remember, phi hat of omega was a Gaussian function, but because it's in the denominator, we can multiply by the inverse of phi hat. And so the inverse of phi hat is the Gaussian, but with a plus sign. Right, so this is what we get here. We obtain that the set of functions in the RKHS is a set of functions f in L2 continuous, such that the integral over the frequency domain, so over omega, of f hat of omega squared times exponential sigma square omega square over 2 is finite. And when it's finite, this number is up to a constant, the square norm in the RKHS. All right, so what can we say about this? Something important to notice is that for this to be finite, you see that you have an exponential of omega squared that diverges to infinity very quickly when omega gets large. So if you want this thing to be finite, then f hat of omega has to decrease when omega gets large very quickly. It has to decrease at least as fast as the exponential, right? So that when you multiply f hat of omega squared by the exponential, the product of the two, goes to 0, so that the integral is finite. So if you've done, you can check on Wikipedia or some textbook on signal processing or functional analysis, you can easily check that the set of functions whose Fourier transform decreases exponentially to 0, in fact, is exactly the set of functions which are infinitely differentiable, right? Because, just to clarify, you may know or you may remember that the Fourier transform of a derivative is omega. So the Fourier transform of the nth derivative is omega to the n times f hat of omega. And so when you expand the exponential as a convergent series, as a sum of omega to the k over factorial k, what you need here is that the Fourier transform of all the derivatives of f has to be finite. Right, so this is a parenthesis, but for those of you who have manipulated Fourier transforms before, but for others, just trust me that when the Fourier transform decreases as fast as an exponential, then this means that f is very smooth in the sense that it must have infinite, it can be infinitely differentiable. And all the derivatives must be in L2, and then this norm in the RKHS can be expressed as a sum over all the derivatives of f of the L2 norms of the derivatives, weighted by some coefficients. All right, so maybe one just take-home message is that the RKHS of the Gaussian kernel is a set of very smooth functions. And the norm in the RKHS, you see, if you want the norm to be small, then really f hat of omega should be very small when omega is large. So this is a space of functions. If you limit the norm in the RKHS, like when you do kernel regression or SVMs, we look for functions f with a small norm. Then this means that the functions f with the small norms are the functions such that f hat of omega is very small as soon as omega is large. So this is a notion of smoothness. We work on very smooth function. where the smoothness is defined in terms of how the Fourier transform looks like. And we want most of the Fourier transform to be concentrated around low frequencies. A second interesting example is the Laplace kernel, which whose definition k of xy equals 1/2 times exponential minus gamma times absolute value between x and y. So you see that in terms of function, it looks quite similar to the Gaussian kernel. The only difference is that, I mean, apart from the gamma and sigma, etc., the only difference is that there is no square here, right? In the Gaussian, there is x minus y square. Here, there is no square. So in terms of function, in terms of computation, it's the same. Now the question is it the same in terms of RKHS? And the answer is no. Let's do the computation here. So first, this is a translation invariant kernel. It depends on x minus y, so we can associate a phi to this kernel, which is 1/2 times exponential minus gamma absolute value of t for phi of t. We can compute, so this is an integrable function. We can compute the Fourier transform, which is also integrable. It's equal to f hat of omega equals gamma over gamma square plus omega square, left as exercise. And from this, we can characterize so we can conclude that k, the Laplace kernel, is positive definite because f hat, as you see, is a positive function of omega because of the omega square. And we can deduce the RKHS, just like before, as the space of functions in L2, such that the integral of f hat of omega square times the inverse of phi hat, so times gamma square plus omega square divided by gamma, is finite. All right, so compared to the Gaussian kernel, we see that we have a similar phenomenon in the sense that for this to be finite, we need f hat of omega to decrease, so that when you multiply it by omega square, the product converges to 0 and it's integrable. But we see that the decrease to 0 has to be polynomial here. So we need f hat of omega to decrease at least as fast as 1/omega, whereas for the Gaussian kernel, it was an exponential because it was multiplied by an exponential, which increases much faster than omega square. Right, so as before, I said before that it's well known that functions such that the Fourier transform decreases exponentially are infinitely differentiable. Now, on this case, it can be shown that the functions f such that f hat omega times omega square is integrable are exactly the functions which are in L2 and differentiable and with derivative in L2. But it's only the first derivative, right? And when it's the case, this norm, which is finite, can be written thanks to Parseval equality that allows us to rewrite the L2 norm of f in terms of the L2 norm of f hat. We can show that this norm in the RKHS, so the square norm, is the L2 norm of f plus the L2 norm of its derivative. Right? So this may remind you, this is what's called the Subalif norm, a bit like what we saw with the green kernels. Okay, but so maybe the only thing to remember from this example is that this is a positive definite kernel that looks in terms of function a bit like the Gaussian kernel, but that creates an RKHS which is much less smooth because, for example, here, the functions just need to have one derivative. And in the RKHS norm, what matters is just the norm of f and the norm of its derivative, and then there is no more constraint. Whereas for the Gaussian kernel, we have constraints and contributions in the norm from all derivatives. All right, maybe a last example is, instead of starting from a kernel and then thinking of what is the RKHS, sometimes you can use the theorem to start from an RKHS you may want and go back to the kernel you can use for that. And here I just give an example of what we could call a low-frequency kernel, which is a kernel that defines an RKHS where all the functions in the RKHS are functions whose Fourier transform is bounded, meaning that f hat of omega would be equal to 0 outside of an interval of frequencies between minus omega and omega. So in signal processing, this is something that you may have seen if you studied that before. Sometimes you call that a low frequency filter. Say that you have a function and then you constrain you create a new function that mimics it, but that stays in the frequency domain in a finite range. Right. So if you want to do that, then again we can come back to this theorem and say how to make an RKHS such that the functions in RKHS should have all their frequencies constrained in some interval, meaning that f hat of omega should be equal to 0 as soon as omega is larger or smaller than some values. So for this to happen, it suffices to choose a phi, so to choose a kernel or a function phi, such that phi of omega is equal to 0 outside of the range you're interested in, because then this would constrain f hat of omega to be equal to 0. Otherwise, in this equation, you would have a non-zero term divided by 0 that would diverge to infinity. Right. So the question is just how to, can we choose a function phi that is 0 outside of a given interval, and then inside of the interval, this can be whatever we want. But for example, we can set it to a constant, in which case the norm of f would be just the L2 norm of f hat. So this would be just the L2 norm of f by Parseval equality. And so we would create, in that case, an RKHS, which just measures the L2 norm of f, but enforces that f has all its Fourier transform constrained to be in a finite interval. So it's a set of smooth functions, but otherwise, we just penalize the L2 norm of f. Right, so to do that, this can be achieved just by choosing a function phi hat, which is 0 outside of our interval, and 1 over it. And we see that this is a positive measure. So in that case, we would get a correct RKHS. Right, and so this is what's done here. So if you go from the bottom, we define a capital H, the space of functions, such that f hat of omega is equal to 0 outside of a range. Sorry, I use the notation U is for the Heaviside function, but think of phi hat of omega as just the indicator function of the interval minus omega omega. And then in order to derive the kernel, just take the Fourier transform of f hat. Right, so f hat would be the measure. Take its Fourier transform, and by a computation that I encourage you to do, you obtain a formula for the kernel k of xy, which is sine of omega times x minus omega divided by pi times x minus omega. So you see, this function really is not something like the Gaussian kernel or the Laplace kernel. It's not very clear if you started from this function why it's good or not. But here it's just obtained mathematically as the function that creates a given RKHS that you may want to use, because you may be interested to say that, okay, I want to learn, and someone told me that the function to learn, the functional space to work with, is the set of functions whose Fourier transform is bounded and limited to some interval, and then just to regularize by the L2 norm. Then this is what this kernel achieves. All right. So I hope this gave you some, not only some general mathematical results. So we have seen Ergot's theorem and Dorner Theorem, as well the RKHS definition. But also I hope it convinced you that for translation invariant kernels, we have a quite good understanding of when a kernel is positive definite, and even more importantly, what is the RKHS and what is the prior knowledge we put when we choose a kernel which is translation invariant. It corresponds to a function space which can be characterized by, in the Fourier domain, by how we penalize different frequencies and how this translates into the norm in the RKHS. So I'll finish this lesson today by trying to do a short recap of the 3 classes of kernels we have seen in this kernel jungle. So we have seen the green functions, the green kernels, then we have seen the Mercer kernels, and today we've seen the translation invariant kernels. They have similarities, but for each of them, there are some specificities as well. So just a reminder, for the green functions, the kernel were defined as the green operator, the green functions of some operator d star d, where d was a differentiable operator, so like derivative or second derivative, etc. And so we have seen that when we take for k the green function of d star d, then this creates an RKHS, which basically is a Subalif space in the sense that the norm in the RKHS would be the L2 norm, or the inner product in this slide, sorry. The inner product between f and g would be the L2 inner product between some derivatives of f and the same derivatives of g. Then we have seen Mercer kernels. So Mercer kernels initially were defined as continuous kernels, so continuous positive definite kernels over compact spaces. We have seen that they can be expanded over some eigenfunctions of some operators with eigenvalues. And in that case, we can characterize the RKHS as some ellipsoid over inside of L2, and ellipsoid defined over the axis of the eigenfunctions and with size depending on the eigenvalues. And finally, today, we have seen translation invariant kernels, and we have seen the link with Fourier analysis. And in that case, the RKHS is fully defined in terms of f. So f, a function f is in the RKHS when its Fourier transform satisfies some constraint, and in particular, when the norm of the Fourier transform decreases fast enough when you and has to be integrable when you divide it by the Fourier transform of the kernel itself. Right. So this slide characterizes the norm of the of each function in the RKHS. So there are links, there are links between the three things, but I encourage you to, get familiar. I mean, maybe reread the slide so that you now you realize that we have used different techniques. So there are lots of different mathematical techniques, but all of them provide tools in order to understand what some kernels do and what's the corresponding RKHS. All right, so we'll stop here. I will just mention that the next section is optional. You don't have to do it for the master course. But just one word about it. It's a generalization, so it's called generalization to semigroups. I will not do it at all, but basically, maybe I will just jump to the main theorem of that part, which is on slide 322. Basically, it's a way to say that what we have done for translation invariant kernels characterized in terms of Fourier transforms can be done in a much more general setting where we see the translation invariant means that you have a function of the difference, x minus t. And so if you replace x minus t by anything that looks like x minus t, so this anything is a group operation or even a semigroup operation, then you can do the same story, and the Fourier transform becomes Fourier analysis or harmonic analysis on the semigroup. Okay, so it's a bit more general, but mathematically, it's just a generalization. And so in this context, we also have the equivalent of Dorner Theorem, which is written here. So I will not read it; it's too abstract. But suffice it to say that it says that a function phi is positive definite if and only if. I mean, there are a couple of additional constraints, but if and only if it is the Fourier transform of a positive measure. Okay, but then we need to define what is the Fourier transform over a semigroup, what is the Radon definition, what is the exponentially bounded, etc. So there are a bunch of technical things, but roughly speaking, Dorner theorem in the case of R is just a particular case of a much broader concept, which is positive definite functions over groups and semigroups. And for example, if you want to study positive definite kernels over permutations, you may know that permutations, the set of permutations form a group, and so it's possible. And there's been some active research recently on defining positive definite kernels over the symmetric group, so the group of permutations. And this typically uses these types of characterization to talk of the Fourier transform of a function over permutations, right? So of course it's a bit beyond the discourse, but if you're interested, feel free to read this and to check a bit the recent literature, recent papers that discuss these topics. So I'll stop here for this time. Thanks for your attention, and see you next time.